Yeah,
Yeah.
right.
Hey there. Welcome everybody once again to Astronomy Daily Live.
Ingrid's here.
It is 2:01. Ingrid is in the
Ah,
chat.
there's Ingrid.
Nice.
Hello,
Hey there,
Ingrid.
Ingrid. Yay. So yeah, I've got um the Vulcan Atta is back on the panel. Hey there, Atta.
Yes, I am.
All right. Well, welcome back. So
Well,
you've
it
been,
was fun, but it's nice to be back.
it's all, that's kind of the, one of the things that I noticed about traveling is, is that, it's really kind of fun to go there and be there. But the best part is coming home, right? That's like the best part. So yeah, well, welcome back. I'm glad
Well,
you're
it's
in.
a good deal. I should probably be lucky at my age that I have a job at all, much less one that's as much fun as this one.
If you can
Yeah.
combine work and fun, you've got it made in the shade. So you're doing great. Yeah, excellent. And Bobby, hey, what's going on? You've got a different configuration here. What's going on?
Yes. So what happened if you was watching my YouTube videos and also I have just restarted my YouTube channel with some good radio videos. What's happening with the USB port on this left side right here? The problem with it is it's going bad. Now what I can do, so what I did, in order to not overstretch the boundaries, I decided to rearrange my furniture. And what I did is I put the dongle for my keyboard on the left side and put everything else on the right side. Now, just in case this side fouls up again, which I don't think it should, okay? I'm going to have to do when I get my check again is get myself a hub.
Get yourself a hub. Absolutely. Yeah, well, good, good. Well, I'm glad everybody's well. Everything is good here. Yeah, yesterday, as sort of predicted, I was running a little bit late. I actually probably could have done a live stream, but instead, I was just able to relax and just sort of move at as slow a pace as I would want, and that is exactly what I like, for
Now,
sure.
just
And
I don't think you never answered my question back at Joseph's live stream. But how are you loving your RSP2 Pro?
oh, we're there was a short, relatively steep learning curve, but I think it's very, very, very awesome.
And your boss loves it too, right?
Well, he hasn't really had a chance to use it all that much. He actually wants to buy a second one for himself, and
Okay.
and so I'm like, yeah, you probably should. So yeah.
So if he's gonna buy himself another one of those RSP2 or something better than that, then can you take your RSP2 Pro home and try it and get some antennas and do it for yourself?
Well, I've got all the antennas at work. That's all I need at the moment. So yeah, that's where all the work is being done. So yeah, that's really, really great. So last night, I was also able to get onto the sky.
Oh, yeah, that
Hebe. I stared at the
and
asteroid.
that was a
Hebe.
good catch on Hebe.
Well, it doesn't take much. You just have to know where exactly the point. So and I actually had a little bit of trouble. The telescope was not pointing all that well. And so it took me a little extra time, to actually find it. But I stuck to protocol, right? In that, I gave myself about 10 minutes or so to try, to find it, right? I look at the star patterns on my screen and I compare those patterns to star patterns on my chart, and I try to match them up.
And by the welcome Tom and Scudder and Page Master in the chat.
Hey there, everyone. Glad you could come by.
Give me a brief moment. I'm going to get something for Arthur to see.
All right, we'll let you go. You may go.
Hey, speaking of seeing, Cosmic, you would love this Spock cup. It's huge. It's 20 plus ounces.
I think that is absolutely fabulous.
It's creepy. Yes. It's a little creepy, Oh, yeah, his face. Ooh, it's creepy.
Well, he was a pretty serious guy there. So yeah. I think
I'll now show you what you should get for an SDR.
Okay. It's going to show me what I should get.
All right. Go for it, Bobby.
Go.
Well, all right. Okay. Well, this right here is called the RTL SDR. It is a great starter wideband receiver for about $20. Now, it's supposed to have those markings, but I've been overworking it so much I think I took the markings off. So they're no longer there. So I did apologize.
So one end is a USB, and the other end is what?
This is what they call it, the SMA coax port, which let me disconnect this. So this is a SMA here's a coax with an SMA connector.
Yeah.
And what it does, it connects straight to from the antenna to the dongle to your computer.
Okay.
Nice.
Yeah. And what's also good about it, you can try fiddle with it, and if you like it, then you should get yourself one of these. Now, this is a good wideband software-defined receiver. Goes from a kilohertz to 2 gigs. This one only goes from the CB to 1.8 gigahertz.
Which isn't bad either. That's not bad.
Oh no, not at all.
No.
Now there's a way to get shortwave on this dongle. And one of the things, and it's my recommendation, okay, is this up converter. It's called an up converter. All you gotta do is plug up your long wire to this end and a coax on the other to the dongle. Program your receiver to receive the signals coming within the up converter, and you got shortwave.
You mean I can do this indoors?
Well, you need an antenna outside.
Okay.
Yes.
Yeah. That's all right. Usually best.
Well, I will think about that.
Usually best. Yeah. Okay. Hey, I wanted to say howdy to Carolina Sky Astronomy. Hey there, Jim. Nice to see you in the chat.
Great for PageMaster to have the RTL in the RSP-1A. This is an RSP-1, by the way.
Cool.
Nice little box stove.
Yeah. Yeah. All right. Well, cool. So yeah. I'll go ahead, Bobby.
And Jim's got the 1A too.
Nice.
And speaking of SDRs, I am trying out a good new program that's meant that's supposed to be made for software-defined transceivers, but it's also great with software-defined receivers called QUISC.
Cool.
And QUISC can do a good job. And if Jules was watching this video, I cannot believe I didn't do it. But QUISC can easily do it in a factory, and he used to have it in a factory.
Nice. Nice. All right, well, cool. So, yeah, I had a pretty successful night observing Hebe last night. Looked at it for about
Jim, by the way.
2 hours. Yeah, hey there, Jim. Looked at it for about 2 hours or so. It's over in the constellation of Gemini, and so it was already setting, or at least past the meridian when I started observing it, and so I was only able to see it for a couple hours, and then it ran into the house. So that was the end of that. But yeah, it looks. I think the data looks pretty good. Yeah, time will tell. This particular object actually does have sort of a discernible light curve, so I can plot brightness versus time, and I might be able to see it actually rotating a little bit. So we will see. We will see. So that's the primary reason why I want to get this kind of data is because at the moment I don't have any software written that can actually do the analysis on a moving target. So yeah, now that I've got a pretty decent data set, I am going to have to start thinking about how to write the code to deal with that. So shouldn't be too hard to do. But yeah, the goal there is to very, very accurately measure the position of the asteroid and also measure the brightness of the asteroid. So I want to get a light curve, and I also want to see how well I can measure the positions of these things too. So pretty cool. When the moon is full, options are pretty limited as far as that goes. So looking at this kind of object is really, really ideal when the moon's out, because don't really care necessarily about the brightness of the sky. As long as I can see the object, I am good. So Atta, what you got there?
Ooh, caught me. This is my stellar cartography book. Another toy. It's just a toy.
I don't know what that is.
Oh, you don't know what that is?
Well, uh-oh. I recognize that sound.
What is that? It's not coming from me.
That's not me.
At least I didn't think it was. I don't know.
Yeah.
Everything around here goes off at weird times. This is...
Anyway, what is stellar cartography?
This actually is another Star Trek thing. It has all the fictional maps, star maps in it. The book that I'm getting, that I'm really interested in getting, isn't about the fiction. It's about the real life stuff on which Star Trek was based.
Nice.
that's what I'm really interested in getting.
Yeah. Now, what does that mean? The real life stuff.
Well, lots of the technology they extrapolated on in the fiction was actually based on the best science known at the time. And, you know, I'm interested in finding out about that.
Yeah. Okay. Yeah. Well, you know, the what is it called? Communicator is sort of like a flip phone, right? So we've actually gone beyond that.
Yeah.
Now to these guys. So warp factor 1, Captain.
Never mind him.
Never mind
I don't
him.
know how to shut it off.
That's all right. You know, you can't shut up Spock. There's just no way to do it.
That's right.
He just keeps going and going and going. You can't stop him.
Unless I take the battery out, he keeps going.
All right. Yeah. Well, neat. Okay, so that is a star map book based on Star Trek.
That's right. And some of the maps, the only thing I don't like about this, some of the maps in here are just written in Klingon, and I don't know how to speak Klingon,
Come on.
even though it's actually a structured language. It was built like a real language.
Wow.
And there are kids who can speak Klingon, actually.
Oh, wow. Wow. Can you show us a little bit of the inside?
Yeah. Wait a minute.
Do some show and tell. I love show and tell. That's one of my favorite things. So.
For example, here's their, well, I don't know if you can see this because it's not a real, this is the Beta Quadrant. Now let's get to the Klingon maps. Oh, those are great. Ah, here we come. Oh, that's the Cardassian Union.
Okay.
And we've got Cardassian Union. What do I have? Where are those awful Klingon maps? Wait a minute. Oh, and of course, there's Vulcan.
My resolver went out.
And what do we have? Ah, here we go. The Imperial Klingon Empire. There she is.
Very cool. Hey, Bobby, we cannot hear you.
No, Bobby, you sound weird.
Can't hear you at all, Bobby.
Let me do something. Oh, crap.
You're breaking up. You're breaking up.
Yeah.
I can hear the dogs pretty well.
Yeah, they're must be a doggy alert of some sort.
Let's see.
You doing better there, Bobby? Oh, he's trying. He's trying.
Next one too.
Yeah, your video is really, really bad. Oh, he's frozen now.
Yeah.
He's a frozen Bobby.
Yeah.
Yeah. Oh, well.
Yeah, Mike. Yeah.
Yeah. Okay. All right. Well, I'm gonna
faster.
I'm going to continue regardless. So yes, Atta has Spock ears. That you learn something new every day, and so there you go. She's got him there. There we are. That's fantastic.
Yeah, I just wanted to let you know the brief kick out that I just had was the result.
Cannot hear you at all, Bobby. Can't hear a thing. Oh, he's really gonna bang on it now. See, I've got him started. All right. Well, excellent. So, all right. Well, cool. Well, I hope everybody's doing well. Like I said, had a good session last night. Data looks relatively okay. I have to work out exactly how I'm going to deal with the data, but I will. I will. So yeah, I think we're looking at Bobby's potato there. It's just clunking along. Worse than mine. Mine barely runs at all. You know, I got to keep feeding the squirrels to keep it going. So
Yeah, looks like the system's overloaded at the moment.
All right. Well, he's going to continue to work on that. I'm gonna mute him. Just so. Oh, can I? I'm trying to. There we go. Okay. Very good. When he is done with his little shenanigans, he'll come back on here and let us know how all that went. So, all right. Well, very cool. So let's see. You know, the one thing that I wanted to do a couple of days ago, and yes, we saw the shirt. Yes, that's a fantastic shirt. So you got that from Teespring, yeah? Is that right? Teespring.com.
Yeah.
I should see. Yeah, you know, I should probably do a better job merchandising things a little bit, but yeah, the let me actually try to find that over here. The my coworker, who is actually also able to make shirts and mugs and all that kind of stuff, he's still sort of on a learning curve with all of that. So so he's not quite ready to be able to supply me with the kinds of things that I might want. But I do have a couple of things over on Teespring, which I'll post over in the chat, and probably do a little bit more over there. I think these guys, I think these guys are just T-shirts as far as I recall. So, but fun stuff. So yeah, you know, the one thing that I've wanted to get to for a couple of days now was a post that actually Tom posted over on my Discord server a couple of days ago about measuring the sizes of stars using the occultations of asteroids. And I thought that we could probably take a look at that and see what that's all about. So let's get on over there. I'm going to okay. I'm ready to rock and roll. Bobby, are you back with us? I muted you while you were moving around there, so you might have to unmute yourself. I think you've done.
Yeah.
There we go.
Yeah, I'm good. Okay, yeah, my name resolver derped. And I think I just broke a rule too. Because when I banged on it, this bottled water spilled all over my computer and all over my surge protector.
Oh my gosh.
Oh man. Well, you know, you've got to that, you know, like I say, this molecule is absolutely amazing, and it'll get into anything, and it's got a mind of its own. So you know, it saw its opportunity, and it just went for it, right? So yeah. Well, hopefully don't get zapped over there, Bobby. That would not be nice. That would not be nice at all.
Yeah.
So,
Yeah,
all right. Well, I'm going to go ahead and share my screen, and let's take
yeah.
a look
So
at
what
this
happened?
paper.
My resolver dirt and stuff like that. And Ata, can you like show me your book again?
What do you want me to show you my book again? Okay.
Sure.
Because
Maybe you could see this title better. It comes in this great big thing, stellar cartography, Star Trek stellar cartography. And it opens up. Whoa. Opens up, and there are maps on both sides of it, and a big book in the center of it. It's where my book is. God. I'm falling over with this thing here, and I wasn't ready for this. This is the little book that's in the center, Stellar Cartography. It has maps of all the fictional empires. See, even though I am a big fan, I realize it was just a TV show.
Oh,
These are all of the things. My personal
you were-
favorite is the
yeah,
Klingon Empire. Stellar cartography, very nice. And there we are. I guess I should sell this merchandise. You know, I'm all hot for it. So
there you go. There you go. You could be a spokesperson for it.
oh
At
yeah,
least.
sure.
At least.
I could
right?
open up a whole new market for them for geriatrics. You know.
There you go. There you go. Yeah.
Carolina Sky says he's trying to find Vulcan with his telescope.
Well, you know, you
Oh God.
now there actually is a planet around. I think it's I'm trying to remember the name of the star. Is it Delta Eridani? Something like that. That's an actual star, and they've actually found a planet around it.
All right.
But yeah, I don't, you know, it's hard to tell really, you know, the parameters of these planets. But I think they've decided that it's too big, or you know, not an actual you know, planet, you know, that could harbor any kind of life. Let's see if I can find it here. I'm just
I think I should be
doing
good by now. So
doing a
don't
quick
make that
search.
mistake
Yeah,
twice.
40 Eridani A. 40 Eridani A. So let's actually, before we get into the paper, let's just look at 40 Eridani A, which is the star of Vulcan. So let's I can go ahead and share my screen. That da-da-da-da-da-da. And we'll come over here and we'll go up to Sinbad, and let's look at 40 Eridani. 40 Eridani. I think, is that it? 40. It's also known as Omicron 2.
Did anybody seen the new planet that was discovered and they call it Goblin?
Yeah, well, you know, they everybody thinks that these things need you know, proper names. So yeah, that's as good as any other. Let's do 40 Eridani A and just see what that comes up with. Ah, that's what I thought. Okay, so 40 Eridani. So I think this is, yeah, this is definitely visible in the north. It's just, yeah, it's just west of the constellation um, um, the Orion constellation. So yeah, this is that star is visible, at least. The planet, I believe, is a transiting one,
Oh, how
and
cool.
I think I'm not exactly sure how they discovered it, but yeah. Well, I mean, we're going to find out that every single star is going to have some kind of planetary bodies or body um, going around them. That's that doesn't surprise me whatsoever. I think it's extremely cool, but I think that I mean, uh, there's lots of indication that there are planets everywhere, and even some planets that aren't going around any stars. They could just be floating around out there. So yeah, I think we're going to find those everywhere. So yeah, well, Jim, keep trying, and when you see, that actual planet, let me know because yeah, I definitely want to find out about that too. So yeah, all right. Well, since we're here, let's go over to the paper that Tom posted a few days ago now. Wow, back on the 15th. And let's take a look at this. This is kind of interesting, trying to measure the actual angular diameter of stars using the occultations of asteroids. So that's kind of interesting. It's I think we're going to be likely to find that it's some kind of like an optical effect and very, very, very short time scales. When you're doing these kinds of things, you sort of move into time domain astronomy, which is really, really interesting stuff, and you can definitely learn a heck of a lot. So, all right, let's take a look here at this. So this just came out too. Yeah, just about a week ago or so. So let's take a look here. Direct measurement of stellar angular diameter. Now, if you recall, the other day we actually went through the calculation, to determine the angular separation between the two components of HW Virginis. And I think we found it was something like 2.6 micro arc seconds separation. Well, you can do almost exactly the same calculation with stellar diameters as well. And I think that's partially what they're doing here. Now, wow, that's a lot of authors. So, it's, I don't know, when it gets to be this many authors, I'm sort of like, wow, who did the work? And usually, usually it well, can't say usually, but oftentimes the first author is not necessarily the one that does all the work, but is sort of in charge. And actually, that person, I'm not exactly sure
And
who
we're
that
going to
is.
say goodnight to Ingrid.
All right, Ingrid. Take care.
Yeah.
Thanks for coming in.
Yeah, I guess like sometimes what it is when I do start up the computer and start up the Chrome browser, sometimes there's more resources that needs to do and stuff like that before I can do.
All right.
The hell?
Uh-oh. That didn't sound good. Anyway, Whipple Observatory is pretty near me as well. It's just south of Tucson. It's on the same mountain that
Yeah.
The 6.5 meter telescope is up on. They've got a few other scopes up there too. So that's Whipple Observatory. But it looks like this is a collaboration mainly in the United States. I see one UK person here that's it's like now there. So oh, and there's a Spanish person too, but looks
By
like
the looks
most
of that list, I bet you the graduate students did all the work.
yeah, and that's okay. That's okay. Oh, here's some Germany. Here's Canada. Here's Ireland. Okay, so yeah, I just wasn't looking carefully enough. But there, yeah, okay. So that's a pretty good representation there. Nice collaboration. I like to see those kinds of things, and not just have things at one place, but and this is just me. That's a lot of authors. That's a lot of authors. So there's a lot of fingers in the pie there, and well, well, maybe we'll see why. If they're doing observations of occultations, having some resources sort of spread out might be a good thing, because these occultations, for a particular location on the Earth, you'll be able to see 2 or 3 or 4 per year. But when you're willing to travel a little bit, you can expand those possibilities a little bit. And of course, if you know which occultation you want to go see, then you're going to have to travel there to make the observation. So yeah, let's dive in here and see what they're talking about. So the angular size of a star is a critical factor in determining its basic properties. Yeah, measurement is difficult because they're stars. We often say that stars are point sources, that they really don't have any kind of size. But in truth, that's not exactly true. It's just the angular size is insanely small. And yeah, they're talking here about 1/10 of a milli-arc second, or the other way to say this is 100 micro-arc seconds. That's getting really small. Being able to do this well is extremely difficult. But apparently they have found a way. One way to deal with this is to use very large baseline telescopes. Now, it doesn't have to be a single huge telescope, but they can use an array of them and combine all that light for a higher res image. Now, Atta is laughing about something, and I have to find out what.
Newsflash, technology sucks.
Bobby, that is not news. we all know very, very, very well. So yes, we feel your pain. So
Yeah.
so yeah.
Yeah, it's all got to start with a. It's all got to start with a derp name resolving system.
Okay. Well, keep punching at it. We're gonna keep looking at this thing. So
Yeah.
all right. So let's see this. So this asteroid, Impruneta, passed in front of a pretty bright star back in February of 2018. And it just so happened that there was a pretty good chance that that observation could take place at Whipple Observatory. Very, very cool. And yeah, I'm going to have to find out about this system there. Veritas, I can't say that I know anything about that at all. So yeah, definitely going to have to look into that a little bit. So these are 12-meter diameter Cherenkov telescopes. I don't know anything about those whatsoever. So, definitely going to have to find out a little bit about that. That's why I absolutely love, looking at these kinds of papers. In that, there's always these kinds of things where it's just like, I've never heard of that. What is that? But I'm going to resist. We're going to keep on this thing because I want to see how they are measuring the angular diameters of these stars. So let's keep going down here. Yeah, so they're just talking about the asteroid here. The detected photons allow us to find the stellar angular size that best fits the observation, assuming a given radial intensity profile of the occulted star. Yeah, okay. So yeah, it looks like they are using, some kind of diffraction to do that. Angular size. Okay, very, very cool. So yeah, they time of the occultation, the exact classification of the star remains somewhat ambiguous from the spectral data alone. So the diffraction pattern measured by Veritas constrains the uniform disk approximation of the star's angular size to be 0.125 milliarc seconds. Wow. So, very interesting that's about well, it's 125 125 microarc seconds. So yeah, that's actually pretty big. That looks like a pretty big star. And see, so once they have this angular size, if you know how far away it is, you can just do some simple math. The trigonometry that we were looking at the other day. They are using exactly the same equation to get a radius of this star, and they're talking about 11 solar radii. So that's pretty big. It's pretty
Yeah.
big. Let's see. There's some hint of a mismatch. Yeah, I mean, a lot of this, these kinds of things are based on models. So got to understand all of that. Okay. Yeah. It looks like, they're still sort of talking about the data they have and how well it fits their models there. But okay, here's some pictures. So let's see if we can interpret this. Okay, so these are the ingress and egress light curves for both asteroid occultations. Okay, was there more than one? Did I miss one? I must have missed one somewhere.
I think you did.
Yeah. Okay, so there's this one on the 22nd of February that they use this system to observe. So where's the other one? I don't know. All right, well, we will continue here. So T1, T2, T3, and T4. All right, I'm just going to punch forward here. So light curve, so that's A. And let's see, the light curves of that occultation with the best fit diffraction patterns theoretical point source model. Each telescope light curve is normalized respectively, the combined average. Okay. Guess I'm not quite seeing what T1 through T4 is, but this is the measured intensity of the star that they were looking at, and as the occultation starts, you see these bumpy things. That's just diffraction caused by the edge of the asteroid passing right in front of the star, and they're not. Yeah, see these timestamps here are in milliseconds, so they are looking at these things really, really, really fast. They're looking, measuring the brightness of these stars extremely fast. And then, seeing what they do. And obviously, the star is going to dim because the asteroid is passing right in front of it. But before it does that, it goes through this little bumpy phase here, and that's how you begin to understand what the actual size of the star is. You can figure out, what the shapes of these bumps should be based on some size, and then match it up. So very, very cool. Let's see. I'm not quite sure what C and D are. Okay. All right. So this is the ingress and egress of one of the stars and asteroids, and this is the same for a different different occultation. You can see that they've got a lot more data here. And for some reason, they were sampling this like that. Here is a little bit more. I guess how I read this is that this occultation was very, very fast. So what that usually means is that the relative speed between the Earth and this asteroid, it was just very, very, very fast. So to be able to actually catch the occultation, they have to sample really, really, really fast. And it only took 120 milliseconds to grab all that data. So here it looks like the asteroid was moving a little bit slower. And so I don't know if you can actually see that or not, but I'm going to zoom in a little bit more. So yeah, here the asteroid looks like it was moving slower, so they could sample a little bit more, and that's why this looks not as dense as this. It's just because there was a longer time there. So
Yeah.
And yeah, pretty cool. So at least according to this model, the size they get for this star is 125 microarcseconds. So this is 0.125 milliarcseconds. That's what that number is. What I'm doing is I'm just multiplying that number by 1,000, so I can talk about things in microarcseconds. I think that is just absolutely fabulous. Okay, so yeah, well, that's kind of nice. They get the same size for the ingress as they do for the egress. That's good. We like that. That looks about the same too. So about 94 microarcseconds diameter there, which, yeah, that seems pretty big. I didn't see. Whoop. Let's let's unzoom this a little bit. I didn't see how big. Okay, here it is. Okay, so that one took place on May 22nd. Also, going over the same location. So these guys were pretty lucky, to have two asteroidal occultations go, pretty much right overhead, right at the same location, within a couple of months of each other. So
Yeah.
that's pretty lucky. Like I said, yeah,
definitely.
like I said, for any given location on Earth, you'll usually get 2 or 3, maybe 5 of these things per year. But yeah, to have them that close together and in the same place, pretty good. So yeah, I guess they're getting 94 microarcseconds, which at the distance to the star puts the size at about 2 solar radii. So still twice the size of our sun, but wow, that's getting pretty darn small. Very cool. Very, very cool. So yeah, it's just based on the fact that they can sample really, 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 really fast, and they have a model that can predict these wiggly effects here. And if you've got those two things, sure, no problem at all. You got it. So pretty nice, pretty nice. I like it. I really, really, really like these occultations. I mean, they're just fun to watch. But you can actually make a contribution, with some pretty simple equipment. You can make an observation and send that in, and it becomes part of the knowledge base, and that can oftentimes help. The neat thing about this time domain astronomy, when it comes to occultations, is that you can actually determine the shapes of asteroids using occultations, and not only the shapes, but the sizes and the motions. So very, very cool stuff. What you lose if you want to sample this fast, what you lose is not being able to observe very faint objects. You're relatively limited to bright stars, and the more you limit your star list, of course, the more limited you're going to be in terms of occultations. So yeah, what when you might be able to observe several occultations per year, if you don't mind observing 13th magnitude stars. But when you start to limit yourself to 9th or 10th magnitude stars, then the number of stars that you can actually see goes down significantly. So you might get one of these bright occultations maybe every 5 years or 10 years or so. So they were lucky in that they got two pretty bright stars. Let's go back and look now. They got two pretty bright stars in a matter of a couple months. That's just mind blowing. That's absolutely fantastic. So let's see. This guy was magnitude 9.9, and I think the other one was like 10.5 or something. Let's look. 10.2. 10.2. And if we so dared, we could actually just go over and see if Sinbad has any info on this guy. I'm sure it's there. Yeah, it's just a regular old star, though. It just so happened to be at the right place at the right time. So cool. Where is this thing? I don't know. Pretty red. Looks pretty red. Yeah. See it. You can sort of get a pretty decent idea about its color if you look at the different magnitudes. So the brightnesses here correspond to different wavelengths of light, and B and V and G are right in the visible part of the spectrum, but J and H and K lean towards the infrared. And as you can see, they're brighter in the infrared than they are right in the visible. So it's a relatively good guess that this is going to be a red looking star, because there's just more red light. That's all it is. So yeah, you know, a couple names. Oh, but look at that. There's just nobody has um, studied this object at all. It has a couple of catalog names, but nobody has looked at this lonely star. That's not very nice. Somebody needs to do something about that. There's got to be something amazing about this. I think it's still too far north for tests to have observed it. Yeah, well, that's kind of sad. There's just nobody is talking about this particular star. You know, there are probably uh, you know, some kind of people on some kind of planet here looking at us saying, why doesn't anybody write about that star right there? They're probably doing exactly the same thing, right? So, well, it's kind of sad when you know we find a target. I mean, it's not even. Well, I guess it's hard to know if it's a variable star or anything else. Like, it doesn't look like it is. It doesn't even look like there's anything at the location that it's supposed to be at. So, oh, this we'll have to investigate that a little bit more. That's a little. Oh, those coordinates are totally wrong. Yeah, see, that has put us at a right ascension and um, declination of 0, which is just totally wrong. It's over here. So yeah, Aladdin Light is failing us here a little bit. Let me try to open it in a new tab. Maybe not. No, it put us right back there. Now, for some reason, the little script, yeah, I think I probably know what it is. If you can see in the lower left, do you see the link there? It says target equals BD minus 07, and then there's a space. You cannot do that in HTML or JavaScript. So that's probably where it's failing, is that it's just not able to get the right target. That's too bad. I wonder if we can just sort of zoom out here and see if there's anything interesting. It looks like there's another bright star next to it too. So yeah, nobody has looked at that star except with this occultation, and that is really neat, right? This star has not really been studied all that much. I guess there's a distance measurement here. Okay, well, that's good. But now we have a pretty good idea as to how big it is. It's pretty cool. Let's see this other one. This one was, the second one was a little bit brighter. And of course, it was occulted by a different asteroid. So now the asteroid is Penelope. Well, let's see if this star has any fame associated with it. I doubt it. It's just a star that was in the right place at the right time. That's how those things go. But we'll look anyway for sure. Okay, well, they're calling it a high proper motion star, which means, you know, it sort of appears to be moving fast. And yeah, you know, if you look at the motion along declination there, 50, almost 52 milliarc seconds per year. Now that doesn't seem like a lot, and you know it really isn't. But you have to also consider how far away these things are and all of that. So high proper motion stars usually indicate that they're nearby. Not necessarily though. So all right, well let's see if there's any oh, there's one reference. Wow. I'm impressed. And pretty close. I think the other one was something like 800 or 500 parsecs away. So this is about half the distance. Cool. Well, let's see what this reference is here. Yeah, I think I just do that. The K2 Ecliptic Plane Input Catalog. Wow, so this star actually made it to or on the Kepler-2 mission. Wow, well that's pretty special. That's pretty nice. That means that we could theoretically probably look at those images. So that's pretty nice. Let's see if we can get anything out of this here. I should have gotten the name of this. Oh, in fact, we've got it right there. Good. Let's see if we can find this in this paper. Probably not. My guess is that it would be in some kind of online list. I don't think that they're going to publish a list of 138,000 targets, but they could publish a list somewhere else.
Check out the chat.
Let's see if they do.
Page Master's coming up with some stuff from Stellarium.
Oh, cool. Let's see. I'm cool. The transit time is 23 hours 26 minutes. I don't know if I'm understanding that very well. Because that's just a regular old star. There isn't necessarily, I don't think, any transit info there. But okay, well, cool. I'm just going to continue here. So cool. So Kepler took a look at this thing. Yeah, let's see if we can find it. Let's just do.
And before you continue, I know you don't have an ad blocker on your Chrome browser, but also, do you have an ad blocker on yours? If you don't, I'll just get rid of it, okay? I'll just get rid of it. Okay, I'll get rid of it when we get done here.
Okay. Okay, well, I'm not having any luck with that at all. I did a search for 278 in this paper, and it's not here. So let's sort of see. This might just actually point us to like a database or something. Looks like, yeah, maybe so. This is probably getting a little bit too much into this. It's looking more and more complicated as we go here. So yeah. Well, apparently, and I don't think I'm going to spend too much more time looking for it. But apparently, this star was observed by Kepler. So, yeah, it might be interesting to investigate this a little bit and see if there's any light curves or anything like that. Um, so, well, cool. I mean, it looks like they've got quite a bit of data here. These things with the um, plus or minus things here usually indicate some kind of data, where these straight lines are usually some kind of model. So, all right, we'll keep going here. Yeah, there's just a lot to absorb. So, okay, so here's just some um, population data of sorts. You can plot temperature versus radius of the star, and you see these kinds of really interesting shapes and trends and concentrations. So the the cooler stars tend to be small, and the and there's a population of cool stars up here that is very large. So yeah, what is going on there? And then you've got these really bizarre structures where for some reason there's a concentration of stars at about 5,000 Kelvin and about 10 solar radii. And it's like, well, why is that? I don't know. Kind of interesting, though. Not quite sure what the difference is. Oh, okay. So this is Kepler data, the original mission, and this is K2, which of course is the second Kepler mission. When they, I think K2 primarily occurred because the one or two of the it's not the gyroscopes, but it's the pointing mechanisms failed. So Kepler, the satellite, was only able to do certain things, and in extremely limited ways. But they were actually extremely successful in actually sampling more data. So that's why I think these look different, because the samples are slightly different, and it looks like there's a lot more here than here. But yeah, why are there differences here? These shapes are sort of the same, but there are some differences. Here's a nice smooth curve here, where this is kind of sharp turning. So yeah, and why does it have this kind of a distribution? That's a really interesting, to plot things this way. And it's just showing a correlation.
Saying if you said 10,000 Kelvin, then this is a spectra class B.
Yes, I would agree with that. Yeah.
Yeah. And also, don't go on a bad technology day and don't get an ad blocker.
Okay. Well, it's hard to avoid those kinds of days from time to time. So you just have to, muscle through it. Um, I tend to make up all kinds of new words. So, it's creative.
You know what's a good song for it that actually resembles a bad technology day? Now, I don't know who sang it, but it's called Straight Tequila Night. And so I guess what happens when you take a lady to a straight tequila night and she'll be thinking about her ex, she's gonna be wrong like crazy. You don't know something?
That is very, very true. Very, very true. I would heartily agree with that. Anyway, yeah, these kinds of relationships are just absolutely amazing. I don't know how I don't know how Kepler measured solar radii. The only way that I can think of is that they were looking at the transits, and they were able to measure the sizes of these stars via the transits. Is Wow, but that sort of implies that we've observed
Okay.
a
Straight
lot of
Tequila Night,
transits.
John Anderson.
What are we looking at here?
Yeah, I was telling Straight Tequila Night by John Anderson.
Okay. John Anderson of Yes?
Well, John, I think it's just John Anderson.
Okay.
Yeah.
And what was the name of the song?
Straight Tequila Night.
Straight Tequila Night. Yeah, that will do it. Anyway, so yeah, really, really interesting relationships there. Let's keep going. That was a great picture. Yeah, so here's just showing distributions in different ways. I guess this is still okay. Yeah, here it's showing. I'm not exactly sure what these designations are, but it's just showing distributions, temperature versus the number of stars that have that temperature. So you can see really interesting structures in those too. We astronomers, man, we love to plot things like this. This is our thing. Showing these moderately interesting relationships that help us make our models, right? Because if we can see relationships, we can see patterns, and it's the patterns that are sort of the basis of all these algorithms and all these models. So, all right, let's keep going here. Stellar classifications, that's neat. Log of the surface gravity versus temperature. So, and it's reversed. See, that's another thing. These astronomers, they do these tricky things like this.
So Pagemaster has a release of a press kit of the Kepler.
Oh yes.
Is that the telescope, Pagemaster?
I would think so. Yeah, the spacecraft. Yeah, that's a really, really, really great place to start. To find out about the Kepler mission, which it's just mind blowing, absolutely mind blowing.
Oh yeah.
Yeah, and I mean, wait till TESS really gets going. It's going to be absolute mayhem, because we're going to be finding, not only thousands and thousands and thousands of planets, tens of thousands of planets. We are.
It's going to be data super overloaded, like over 9,000.
It's going to be absolutely crazy, and in fact, it already is. So terabytes and terabytes and terabytes of data, and these lots and lots of things to look at, and new things that we have no idea yet what we're going to find. And those are the exciting things, for sure. All right. Yeah, so Tesla's going to be amazing. LSST is going to be just so over the top insane. They're talking about over 1 million event events every single day that we'll have an opportunity to observe. But I mean, who can observe 1 million events a day? There's no way to do it. So yeah, it's just we're very, very close to the threshold where we are just going to be so overloaded with data. It's going to be crazy.
Yeah.
And we already are. Kepler was sort of the beginning, and TESS is just going to be so over the top. All right, well, cool. So that's absolutely great, but I really didn't see our guy in here anywhere. So my guess is that we probably have to go to the Kepler site and go through a database of some sort. Although I'm seeing things here, but yeah, I don't know what exactly they're referenced to. So, all right, let's get back to the original paper here really quick. I do realize that I'm going a little bit late, but astronomy is so incredibly distracting. There's just so many paths. Okay, so here we go. Angular size measurements and stellar radius estimates compared to those available in literature. Okay, nice. Okay. So here, I don't know if I'm not sure if I'm. Okay, so these are for the 2 stars. Duh. Okay, I gotcha. So, all right, yeah. These again are kind of interesting plots showing different kinds of relationships here in different surveys. So, all right, interesting. They've done their homework. Yeah. Yes. Well, and that's exactly what I was just saying a while ago. Is that 7% of the, well, they're actually quantifying that here. 77% of them have greater than a 20% chance of being seen at any place. So very cool. Yeah. Okay. So they're saying 5 occultations a year. I can agree with that. for 10th magnitude stars, almost one a week, they're saying, for 13th magnitude stars. Okay. That's a little surprising.
So Page Master just released the link above the NASA Exoplanet Archive.
Awesome. Yes, yes, yes.
And Page Master, if you so inclined, why don't you join the Discord server for Astronomy Daily Live? There it is. And join my radio server for my Discord server for Radio People.
Yes, sir. Do it. Yeah, get onto the Discord, Page Master, if you aren't already. And you know, my server isn't like extremely active, but it's relatively active, and I try to post things there at least a few times a day. And there's usually, you know, some pretty interesting conversations there too. So definitely, you're of course more than welcome, you know, to get on over there and do that. So, all right, well, I think for now, you know, I think I'm going to study this a little bit more, because I'm kind of interested in seeing exactly what they were up to. And in fact, there it is. So yeah, here's actually how they did it. So yeah, I'm gonna dive into this a little bit, and maybe we'll continue to talk about this next time for at least a little while, because yeah, I'm kind of interested in seeing what they're up to. But I think I've pretty much confirmed that, you know, they're sort of combining being able to measure these stars very, very, very fast, and combine that with, you know, the fact that they are going to have, you know, some kind of diffraction along the edge of the asteroid, and that's what they're seeing in the wiggles. So very cool. Very cool. All right. Well, I am definitely going to get out of here for now. So thanks everybody for coming in once again. I know it's past somebody's bedtime, so it's almost past mine too. So
yeah, I know it's definitely way past Otto's and stuff. So
I totally agree. So yeah, let's get on out of here for now. I'm gonna check chat one more time really quick. And yes, the pumpkin, you know, we don't want to see that here. We don't want to see that here. You know, I tolerate a little bit of radio stuff, but pumpkin, no. We're not talking about pumpkins. So, all right, everybody. Well, take care. I will see you in about 22 and a half hours. So have a great evening, a great day, and hold on to your hats, because we are spinning fast. All right. We'll see you later. Bye.
Later. Live on the prize.